channel. So we continue in looking at the component of the transformer architecture like we started the last time. So this time around I want to look at the embedding. You will see that both the input and the output, the two of them are fed into the embedding. So what is this embedding? That is the essence of today. So let's look at the embedding operation. I'm going to take my time to explain this. Now, first, if you have like a text, we have a text that you want to input. Let's say we have, this is our input text, and that text is transformer is the next state of the heart in vision. Okay, research. Right. So if I have this text, now this text, input text, is going to be broken into each token. So if I decide my token is a unigram, so I'll take transformer as one token. Okay, so what I will do is I'll create a dictionary that has a mapping of this particular token, the transformer. It's not copying, so I'll take transformer. I will get a particular value as the key. So let's say I want to use an integer 67 as the key, and the value is going to be the transformer. Okay, for that, so I have a comma, then his, I can take another different unique key, and I will say is the value. Then the next is D, and I can take another unique value 78 this time around, and I will say D is, so you get the gist. So I'll continue like that until I get to the final one, which is research. So research, and I'll say okay, I want to use 79 for research, and I'll map that to research. So this is the tokenization that normally happens in natural language processing. The same thing is repeated, similar thing is repeated in vision research, but I won't go into detail of that. You break your image into patches and you extract the patch, which is a tensor. You flatten that tensor, and that becomes your vector. Okay, now, so what's happening here is, now you now want to take each of these values, 67, 56, 78, 79, which are representative of all these tokens, and you want to represent them as an embedding. Okay, so now what do? Now I've simulated that here, so let's generate an input array, which is using the np.random_int. So what this is going to generate for us is a tensor that has 3 rows and 5 columns. So the 1000 here means generate values between 0 but not up to 1000. So from 0 to 999. So if you check the input array, you will see that the values that we have there is between 0 and 1000, but it can never reach 1000. So if we run this again and you rerun this, you will see that it generates another different values, but it's going to be between 0 and 1000, but it's not going to reach 1000. Okay, so that's what this gives us. So we have our input array. Now you can, as you can guess, you can easily understand that each of these int value is a correspondence of whatever tokens we have on the left here. So this 888 could be transformer, this 29 could be E's, this 156 could be D, and so on and so forth. Now, one important thing we need to understand here is this 1000, meaning we are generating value from 0 to 1000 or 0 to 999 inclusive. It means that that is the size of our vocabulary. What it means is that we cannot expect any integer that is like 2000 or 3000 or 4000, because our vocabulary has limited that the number of unique keys, possible unique keys that we can have fed into our system cannot exceed 1000. So this is very significant. So that's our vocabulary size. Okay, we may not use all the 1000, but it cannot exceed 1000. Okay, all right. So now we go into the code, into the keras. So we're creating a sequential class, and we are adding the embedding layer. Now, so this is the embedding layer implemented for us in keras. The first thing that it takes is our vocabulary. Okay, it takes in the vocabulary so we know how many do we expect in the vocabulary. So that's the input dimension. So the input dimension gives us the total numbers, possible values. Now we have the output dimension. Now this output dimension is an hyperparameters. We can decide to put 2, we can put 3, we can put any values there. Now what this is saying is we want to convert each of these values here into a vector. Now the size of that vector, what is the dimension of that vector, is what we're specifying here. Okay, now the input length that we have here is to tell us as you can see, tell us the number of rows that we're expecting. That is the number of instances that we're expecting in our input array. So in this case we have 3 rows, so the number of rows that we're expecting, that is the input length. Okay, so this is the input length. We specify this as 3. Good. So now I'm regenerating the input array here. Now we compile the model, then we now predict our input array. By the time we do that, we see what it gives us. Now let's inspect the component. So this is our input array. So each of the values integer. Now this is the output array, that is the output of our embedding. So this is our embedding representation, and let's see what's happening in this embedding. Now as you can see in this embedding, the first row here, this list is corresponding to this 943. This second one is corresponding to this 748. This 837 is this one. Okay, now the first list here, the first row of this multidimensional list, okay, so of this tensor corresponds to the entire of this one. So this is what it corresponds to from here. Okay, so this represents that first row in this place. So each of them has been turned into a size 4 because we specify that our output dimension is 4. So that is why we have 4. Let me do something quickly. So let's say I want it to be size 3. I want the output dimension to be 3. So I just change this to 3. So if I rerun this, so it's going to give us an output dimension that is, what is this saying? Predicts the input is 3. So let's see. So this is, so the output array, okay, so that is going to give us 3. So we can see that it's now representing each of these using just three vectors, three dimensional vector. Okay, now so that's essentially what the embedding layer does. It takes in integers which are corresponding to our vocabularies, which map to each of our vocabularies, and it represents them with a particular with a vector representation with a fixed size, irrespective. So whether we have transformer which has like maybe 8 characters, H is which has just 2 characters, or A that just have 1 character, it doesn't matter. It represents all of them using just one fixed size. In this case the size is 3, so each of them is represented with a fixed size vector. That's the essence of that. So we don't have a variable length vector. Okay, because this is representing transformer, we don't say that, oh, this one now has longer length than the one that is just representing A that has single character. Okay, now one final thing is for us to inspect. Let's say that we have 157. So I'm going to use this and quickly create another input array. Let's say we have duplication in the array, so let me say our input array. So I'm going to take this one up. So I'm going to say create my input array as np dot array, and I'm going to put in that. So what I will do now is I will now manually change this to 157, so that you will see that the vector representation of the first one here should be the same as the vector representation of this, because they are both referring to the same value. So I'm going to run this. So I have the input array changed. I've already commented out this. So this comes in now. So now I've run that. So let's see the input array. So these are both 157, 157. So let's now see the output array. So this is the output array. Now as you can see, you will see this one represent the first 157, which is here. Okay, now the last 157 is represented with this, so you can see. Okay, all right. So and if you can see the two values, you will see that this is the same as this is the same as this so that means it's actually unique. It's actually unique. So it's actually representing the unique values. All right, so that's what I wanted to show us there. And if you want to do it in precision mode, if you want to actually see it in precision mode, you can just use equals and put it in 2 variables, and that would. Okay, so that is that is the embedding layer of the transformer architecture, which is a very important component. Okay, thank you very much, and see you in the next one.